Alrighty, this is our last topic for the first unit of BC Calculus, and it's kind of broad, and when there are a few examples, this will probably be one of the longer videos here, but let's jump into it. So we're going to go ahead and study improper integrals. And again, it's a broad subject, and there are really two types of improper integrals that we're going to look at. The first one are integrals that are infinite, meaning you have some sort of limit where either the upper or the lower, maybe the lower one's negative infinity to 6, or you end up going negative infinity to positive infinity, or one of the most common ones you see is 1 to infinity. But either way, one of the limits of integration is infinity, and this is called an infinite integral. The second type of integral is called a discontinuous integrand, and it's where you're dealing with some sort of function that the limit itself would cause the function to be undefined. And we're going to relate this back to area a lot, and I think you'll see why it ends up being undefined in certain areas. There are also two vocabulary terms that you need to be comfortable with. The first vocabulary term is if an integral is convergent. And if it's convergent, it means if you have the integral from something to something else of a function, then there's actually an answer. We'll call it maybe L. So it actually has an area under the curve. Versus if your integral is divergent, then after you calculate the area, you realize that the area is either infinitely large, infinitely small, or you really just can't calculate the area at all and it doesn't exist. Okay, so let's go ahead and get started. We're going to take a look at infinite integrals first, and then we'll tackle the discontinuous integrands at the end. So first example. It's super common, again, I noted before, to integrate from 1 to infinity, and we'll see more about why once we get into series and sequences, but we're going to take a look at two of these that go from 1 to infinity and then try to generalize what's happening. So, if we're dealing with something like this, we realize that when we integrate, we're not going to be able to plug in infinity. And in order to deal with that, we can actually replace infinity with a variable of your choosing. It's common to see t. I think a lot of the AP tests use a and b, and I'll just stick with a, first letter of the alphabet, why not? So instead of going from 1 to infinity, we're going to go from 1 to a of 1 over x squared dx. But we're going to look at this integral in terms of a limit, and particularly the limit as a goes to positive infinity. So think a second, and we'll get back to the actual calculus piece of this, but think a second of what's happening with that graph. The graph of 1 over x squared is super similar to a rational function, except because you're squaring the denominator, it's going to cause all those negative y's to become positive. At this point, we're integrating from 1, which is right about here, it's the point 1 comma 1, all the way out infinitely large on the x-axis. So ultimately we're calculating the area of here and all the way out that's getting smaller and smaller. And the question is, will this graph eventually get so close to the x-axis that the area is negligible and stops building? Or will that piece stay a little bit higher above the x-axis, and when you keep adding on areas and have it be an infinite area, so the integral will diverge? So let's see what happens. Alright, we can keep our limit here and calculate the integral as normal. Alright, we know that 1 over x squared is x to the negative second, and we can continue. We know it's the limit as a goes to infinity of, well, x to the negative second. We'll add 1 to it so it becomes x to the negative first. We negative a negative 1 in front to offset, and then we go 1 to a. Right, I'm going to take a second to factor out that negative 1, and we end up looking with something like this. Negative 1 times the limit as a goes to infinity of, and then we have a to the negative first minus 1 to the negative first. So still that usual process. We plugged in the top limit first, and then the bottom, subtracting the two. That's our first fundamental theorem of calculus. Nothing too bad. Continuing down. Negative 1 times the limit as a approaches infinity, or as a converges to infinity, might be another way to say that. 1 over a minus 1. Okay? And we know if we take that infinity and we think about substituting an infinitely large number into a fraction, 1 over an infinitely large number tends to 0. So we end up with negative 1 times 0 minus 1, which ultimately negative 1 times negative 1 comes out to be positive 1, and we actually get an answer. So we say that this integral converges, and in particular it converges to negative 1. Another way to think about it is that area under the graph up here. That area, if you summed it up, would have a grand total of 1 square units. Alright, so it's not too bad. I think the only real difference is the notation and actually keeping the limit all the way through. Let's take a look at another. Okay. This one we're given almost exactly the same situation, but now we're looking with the equation 1 over x. Again, visualizing a graph is always a good idea. This one is just a rational function. It looks something like this. Okay. And it seems to be pretty much the same situation. We're starting at 1, 1, and we're summing the area under the curve. So maybe it'll come out to be something close to positive 1 again. Well, here we go. Similar idea as before. We're going to deal with the limit as we'll keep using a as a tends to infinity. The integral 1 to a. And then we'll keep this as 1 over x because I think we're pretty comfortable with this by now. We know if we take the antiderivative of 1 over x, we come up with the natural log of the absolute value of x. Oh, no integrand there. So we end up with natural log absolute value of x from 1 to a. And then we can substitute. So still looking at the limit as a goes to infinity of the natural log of a minus the natural log of 1. And think about substituting an infinitely large number in for a. It might help you to visualize that graph of the natural log of a. And if you can't keep the natural log graph straight, try a couple numbers you know. You know if you plug 1 into any log or natural log, you get an output of 0. And if you plug e in, so let's see, it's 1, 2, here's 3 over here, so e lies somewhere in between. If you plug e in, they undo each other and you end up with 1, and it might help you sketch a graph that goes up like this. So here's your graph of natural log. And notice it's growing without bounds, so it's going to continue to grow up and up and up. So if you substitute in an infinitely large input, your output is infinitely large as well. So we end up getting something that's infinitely large minus, well, the natural log of 1 is just 0. And so we see that our area is going to be infinitely large here, and therefore we can conclude that our integral diverges. Okay. It's kind of strange actually that 1 over x versus 1 over x squared, you see that difference in the two where 1 over x squared converged and 1 over x diverged. And in fact, you can keep exploring it. 1 over x cubed, 1 over x to the 4th, 1 over x to the 1/3 power, so on and so forth. And eventually you'll find a correlation. And we call this correlation the p-test for integrals. And this p-test for integrals states that if you're dealing with an integral from 1 to infinity of the function 1 over x to the p, where p is some sort of power, so first power, second power, 2/3 power, so on and so forth. If your power is 1, and we just looked at that one, we saw it diverged, or it's less than 1, then it tells you that the integral will automatically diverge. Versus if your power is any number greater than 1, 1.1, 2, 5, 500, anything like that, the integral will converge, and interestingly enough, it'll converge to 1 over p minus 1. There's a nice proof behind that too, but it's outside the scope of what we need to do for this class. And honestly, this isn't something you need to recall. You can calculate this by hand, but it is a nifty little theorem. If you remember, though, you go, okay, we're dealing with 1 over x cubed. We go, cool. Not only do I know that converges because p is greater than 1, but I actually know that it converges to 1 over 3 minus 1, which is just 1/2. And it saves you a bit of time in the long run. So it's not a bad thing to commit to memory. Okay, so that was our first type of improper integral, and those were ones with infinite limits. Let's take a look at the second one. Oh, apparently that was a huge lie. We have one more here, and this is a nice example of something that doesn't end up with an infinite limit, but rather ends up with a limit that does not exist. And it goes quickly. So it looks something like this. We use our limit again. I'll continue with a because why not? Negative 2 to a sine of x dx. We take the antiderivative, still keeping that limit out front. We haven't applied it yet. And we know the antiderivative of sine is negative cosine. That negative to offset the negative when you take the derivative of cosine from negative 2 to a. Maybe factor that negative out front. The limit as a goes to infinity of, then we end up with cosine of a minus the cosine of negative 2. And taking a peek, you might not know what cosine of negative 2 is, and that's fine. You don't have to. Because we know if we look at cosine as it gets infinitely large, it approaches nothing. Cosine is one of those sinusoidal functions, right? It starts up here and it just goes up and down and up and down. So as you get infinitely large, it's not getting smaller and smaller, it's just still up and down, up and down, up and down between negative 1 and positive 1. It doesn't approach anything. So this limit right here does not exist. Then we have minus cosine of negative 2. But as soon as one piece doesn't exist or tends to infinity, you can already say that this is going to mean that your integral will diverge. And thinking about the graph of sine, that should probably make a lot of sense because we have a positive area and then the negative area undoes it, and then a positive area and then a negative area, so on and so forth. Alright, now, I'm pretty sure I'm right this time. Now we're looking at discontinuous integrands. Discontinuous integrands have some issue with the limits. Something's going on here, either at one of the two endpoints or something in between. And you'll notice here the issue is actually that 3, because if you were to look at 3 on this graph, there would be no point there. And it wouldn't be such a big issue if there was a hole. So for example, if this was 3 and the graph kind of went up and then there was a hole, that wouldn't have an impact on the area. That's an infinitely small slice, no big deal. However, if this graph goes up and there's an asymptote there and it rises up forever, we could have a case of an infinitely large area, and then we have an issue. This is something you really have to recognize right off the bat. You need to be especially careful in BC to take a look at it and go, okay, wait, is there going to be an issue with this integral? At this point, they pretty much know you know how to take the integral of something, and they're going to try to throw you off, so be very careful. Maybe use the answers to guide you. If you see one of the multiple choice answers that says does not exist or diverges or infinity, you're like, uh-oh, wait, something weird is going on. Okay, so let's take a peek at this. We know 3 is going to have an issue. And again, going back to that graph, there's no issue at 0. Maybe you don't know what this graph looks like, so we can make it up. Here's 3, and it's going to do something, and then who knows what happens at 3. Alright, well, let's use our same limit trick. The limit as a approaches 3, and we'll come back to that in just a second. We know this is a square root, but it's on the denominator, so maybe we think of it as like 3 minus x to the negative 1/2 power dx. Integral from 0 to a. Just be careful with the limit. If there's nothing as a approaches 3 and there's nothing on this 3, then it means we want to know the limit as we approach 3 from both sides. But we don't. We're only interested as we approach 3 from the negative side, right? We're approaching from the negative numbers over here, so 3 to the negative. So we do actually need that one-sided limit in this case. Okay, let's continue evaluating. We have the limit as a approaches 3 from the negative side, and we can actually take the antiderivative in this case. We would have to add 1 to the power, so we know it'll become 3 minus x to the positive 1/2. When you take the derivative, the 1/2 would come in front, so we need a 2 to offset it. And also when you take the derivative, remember the derivative of the inside would be on the out, so you'd end up with a negative there, so I think we'll need a negative 2 here, just to offset everything to get us back to what we started with. And then we go from 0 to a. Okay. Continuing, let's just go to the right so we don't run out of room. The limit as a approaches 3 from the negative side. I should probably factor out that negative 2 as well, just so things don't get too weird. And then we end up with 3 minus a to the 1/2 power minus 3 minus 0 to the 1/2 power. Okay. Continue evaluating, negative 2, and then at this point we go, okay, as we go from the negative side of 3, well, it doesn't really matter in this case. I don't think. Let's take a peek though as we go through. I guess the question becomes, can we plug 3 in? And I think we absolutely can plug 3 in. So remember, if there is no negative here, we can actually take this 3 piece and plug it right in. And if that works, then that automatically implies that the one-sided limits are equal. So let's see what happens if we plug 3 in. We end up with 3 minus 3 to the 1/2 minus 3 minus 0 to the 1/2. Okay, which really just becomes negative 2 times the negative square root of 3, which becomes 2 squared is 3. And I believe we're done here. This integral converged. Nothing weird happened when we looked at that one-sided limit. We're good to go. Here we go. Next problem. This one is a little bit more strange. We look at the two endpoints of the limit, and we see there's nothing wrong with negative 2 when you plug it in, and there's nothing wrong with 3 when you plug it in. However, there is another issue somewhere in this limit, because remember, we are again trying to calculate the area underneath the curve. So if you look at that graph of 1 over x cubed from negative 2 to positive 3, you might not know what the graph looks like, that's okay. It'll go up here. But then we know 0, something weird happens. We can't plug in 0, there's a discontinuity there. So maybe this graph goes up here and then, I don't know, comes up here and does something like this. Well, how do we deal with the area under there? And again, it comes down to limits. You have to be super careful here. Notice that you could actually calculate the integral just from your AB knowledge, right? You could say, okay, this is the same thing as x to the negative third, so the integral is negative 1/2 x to the negative second from negative 2 to 3, and if you plug those in, you'll get a number, you'll get a numerical answer. However, it could be wrong because you didn't take into account the discontinuity. In order to take into account the discontinuity, we can use our property of integrals and say, this is the same thing as negative 2 to 0 of 1 over x cubed dx plus the integral from 0 to 3, 1 over x cubed dx. Same thing so far, we just split it into two pieces. And now we can introduce some limit notation. Notice that this first integral, we can switch to blue here, this first integral runs from negative 2, and I'll chase that on the graph, to 0. So we're approaching 0 from the left side. So if we wanted to look at the limit of this, we could say the limit as a approaches 0 from the left side, negative 2 to a x to the negative third dx, plus, and then we have pretty much the opposite. We have this right side piece, this green piece, which is fairly funny if you think about it, approaching 0 from the positive side. So we set up our limit as a goes to 0 from the positive side, x to the negative third dx, maybe I need an integral symbol in there, and then, two different variables. We should probably use two different variables. I'll use b here, so b to 3. Just good to keep it straight. Okay, let's finish this off. We take the antiderivative of x to the negative third, negative 1/2 x to the negative second. The negative 1/2 and the negative 2 undo each other. We're doing all right so far. Negative 2 to a, limit as a goes to 0 from the negative side, plus the limit as b goes to 0 from the positive side of, no integral symbol, getting late apparently. Same function, negative 1/2 x to the negative second from b to 3. Okay. It might help you to simplify this a bit too as we're looking at it. So we have that limit. I think maybe we can just pull a negative 1/2 out here. Again, just making it easier to look at. The limit as a goes to 0 from the negative side of x to the negative second, we know is really the same thing as 1 over, and now we'll plug in a. 1 over a squared minus 1 over negative 2 squared. And we should look at this other limit, but let's take a look at the first piece first. Because the nice part about integrals is as soon as one thing is divergent, right, as soon as one thing doesn't converge to a number, you can stop. You can say one thing didn't converge, therefore nothing converges, and we're done. So if we look at this, this says as a goes to 0 from the negative side of 1 over a squared. Visualize that graph, again, like the rational function 1 over x, but that square will put it positive, so we look up here. We say, okay, well, as we approach 0 from the negative side, what's the graph doing? Well, it's tending towards positive infinity, so we know this becomes negative 1/2 times positive infinity minus 1/4. Bam, we have some sort of infinity in there. We're done. Stop, don't do any extra work. We can just say it diverges. The end. Okay. So this is all I have for you, and hopefully this is a nice introduction for improper integrals. Thanks.